Welcome back to another explainer. We're jumping straight into what I honestly think is the universe's ultimate detective story, the race to solve the hydrogen puzzle and uncover the true structure of the atom.
For the longest time, physicists were just totally baffled by a deceptively simple question. What does the invisible building block of the universe actually look like? Back in the early 20th century, this wasn't just some casual, abstract thought experiment. No, this was a high-stakes mystery about the literal building blocks of our own bodies, and, well, the entire physical world we interact with every single day. We knew everything around us was a multidimensional arrangement of atoms, but nobody could point to any actual experimental evidence showing what was going on inside one.
To figure this out, we need a litmus test. Here's the setup. If you put hydrogen gas in a sealed tube and heat it up to really high temperatures, it emits radiation. But if you pass that radiation through a prism, you don't get some continuous smooth blur of light. Instead, you get these incredibly sharp, discrete wavelengths. Specifically, you get radiation at exactly 6562 angstroms and exactly 4860 angstroms. And here's the kicker. Hydrogen emits absolutely zero radiation between those two numbers. It's like a giant puzzle. Any successful model of the atom absolutely had to explain this bizarre behavior.
Which brings us to Suspect 1, J.J. Thomson, who first tried to crack the atomic code in 1898.
Thomson came up with what famously became known as the plum pudding model. He pictured the atom as this spherical shape, basically a uniform volume of positively charged matter, and embedded randomly throughout this space were negatively charged electrons. Think of it like seeds scattered inside a watermelon. Or, you guessed it, plums baked into a pudding. They were just sitting in there to balance out the overall positive charge.
So the really crucial thing to wrap your head around here is the contrast. You've got this uniform, highly spread out positive sphere contrasted with tiny, randomly scattered negative electrons. The positive charge isn't concentrated at all, it's just this soft, diffuse, uniform cloud. Grasping this exact assumption that the atom is just a soft, uniform sphere is absolutely vital for understanding why the results of the very next experiment were so mind-blowingly shocking.
Enter Suspect 2. Ernest Rutherford, who in 1911 decided to put Thomson's soft pudding model to the ultimate physical test.
To test the theory, Rutherford set up an absolutely ingenious experiment. He took a radioactive source and essentially fired a beam of positively charged alpha particles, which are basically just helium nuclei, directly at an incredibly thin sheet of gold foil. He then surrounded this target foil with a circular viewing screen. Why? So his team could carefully track exactly where these particles ended up after passing through the gold.
Now, if Thomson was right, and the atom was just this uniform cloud of positive charge, those heavy, fast-moving alpha particles should have blasted straight through with almost zero deviation. But the actual results were completely astonishing. First off, yeah, most particles did pass straight through, almost as if the foil was mostly empty space. But then, some particles were shockingly deflected at huge angles. And here is the absolute mind-bender. A few alpha particles actually bounced completely backwards. They literally reversed their direction of travel. Rutherford famously said it was as if you fired a 15-inch naval shell at a piece of tissue paper and it came back and hit you. I mean, this completely shattered Thomson's idea. There's just no way a soft, diffuse cloud could create enough concentrated repulsion to physically bounce a heavy alpha particle right back at the source.
Because of this wild result, Rutherford had to come up with a brand new model. He realized the positive charge in the atom wasn't spread out at all. No, it had to be intensely concentrated in a tiny central region, which he called the nucleus. But then, to explain why the negative electrons weren't just instantly sucked straight into this incredibly dense positive nucleus, he proposed the planetary model. He suggested that electrons actually orbit the nucleus within the vast empty space of the atom, operating exactly like planets orbiting the sun.
It sounds like the perfect solution, right? Well, hold on a second. There was a massive, fatal flaw in Rutherford's planetary model, and it came directly from the established, ironclad rules of classical physics, specifically Maxwell's electromagnetic theory. This theory strictly states that any charged particle undergoing acceleration must continuously emit electromagnetic radiation. And here's the catch. An electron moving in a circular orbit around a nucleus is constantly undergoing centripetal acceleration.
Which leads us to a catastrophic paradox. If that orbiting electron is constantly radiating electromagnetic waves, well, that means it's constantly losing energy. And as it loses energy, the radius of its orbit has to shrink. It starts spinning faster and faster, constantly increasing its frequency, spiraling violently inwards, until
Boom! It crashes directly into the nucleus. Mathematically, the atom should collapse in a fraction of a second. Yet, look around. We know that at room temperature, hydrogen is incredibly stable. It doesn't continuously radiate energy, and it certainly doesn't just collapse on itself. Classical physics had officially hit a massive brick wall.
We desperately needed a fixer. Enter Niels Bohr.
Between 1913 and 1915, Bohr basically ushered in the age of modern physics. He developed a semi-classical model mathematically designed to save the atom from this exact collapse. He didn't just tweak the old rules. He boldly laid down 3 strict, brand-new physical laws for orbiting electrons: force balance, quantized angular momentum, and total energy states. He kept Rutherford's brilliant discovery of the nucleus, sure, but he added these powerful new quantum rules to physically stop the electron from crashing.
Okay, let's actually break down what these mean in physical reality, without getting too bogged down. First up, force balance. Bohr stated that the electric pull from the positive nucleus is perfectly balanced by the outward centrifugal force of the rotating electron. Makes sense. But then comes his most revolutionary rule, quantized angular momentum. Bohr basically instituted a strict quantum speed limit. Think of these as invisible, strict traffic lanes in space, governed by Planck's constant. The electron is only allowed to exist in these specific mathematical lanes, and nowhere in between. Finally, the third postulate simply defines the total energy of these allowed states as the straightforward sum of the electron's kinetic and potential energy.
So what does this all mean? Why does all this complex math actually matter? Well, let's bring it all the way back to our original litmus test. Bohr's incredibly specific rules, these exact quantum traffic lanes, beautifully solve the mystery. By keeping the electrons in perfectly stable, mathematically fixed orbits, he proved exactly why hydrogen only emits those sharply defined discrete wavelengths of 6562 and 4860 angstroms. It happens when an electron jumps between those permitted lanes, and it explains why absolutely nothing is emitted in between. On a much larger scale, this mathematical breakthrough explains why matter is stable enough for us and the entire universe to even exist.
It was an absolute triumph, a real game changer that kickstarted modern atomic physics. But, as with all great mysteries, there's a final twist to our detective story. Bohr's model is ultimately a semi-classical compromise. You see, it was developed specifically for hydrogenic atoms, meaning systems with just a single electron. The true picture of the atom is a fully quantum mechanical affair. The moment you add more electrons, the complex interactions between them cause Bohr's precise, beautiful model to fall short. So I'm going to leave you with this final, provocative thought. If Bohr's groundbreaking model only perfectly solves the simplest puzzle, the one-electron system, what vast, entirely new realms of physics are still out there, just waiting to be discovered to explain the true, incredibly complex quantum nature of all the other atoms in our universe? Thank you so much for exploring this atomic detective story with me on this explainer, and I'll catch you on the next one.